Okay, guys, so this is probably our last video, believe it or not, for blood alcohol concentration, or BAC. We are almost at the last leg of the spreadsheet. Thank goodness. I'm so tired of looking at spreadsheets and numbers and calculations. Please, please, no more, no more. Isn't that a Sabrina Carpenter song? Please, please, please. Okay, so here is QC1 and QC2. This is where we left off, and QC means quality control. All right, so quality control is basically the idea that a lab has made something and it has been given to a person so that way they can analyze it. The reason that we do this is we want to make sure their procedure was the proper way. So what goes on here is that we give them basically a QC and they treat it like a blood sample. So in our procedure, you took out the same portion of QC as you did blood, you added it to a headspace container, you added the same amount of internal standard into that headspace container, and then you put the lid on and you shook it up and you mixed it in with all of the other things that we ran, and we're going to get numbers, and we got to figure out what these numbers mean or how they relate and do they make sense. So what you're going to see with the QC is that there's going to be multiple peaks that are very dominant probably. The quality control sample normally involves everything that the standard includes. So methanol, ethanol, propanol, isopropanol, acetone, the whole gambit of stuff is going to be represented in the QC. Normally, we would report QC values on all of these components, but to keep this simple, we're only going to focus on our ethanol peak. So in this particular type of lineup, what you're going to see is that we're going to go to 5.5. We're going to pull out area for ethanol. We're going to go to 7.9, and we're going to pull out the areas for those as well. And these were the values that came from those particular types of reports. Again, this is not going to match your data. Your data set will be your data set. It will be a little different, but it gives you at least a kind of gist of what's going on. So this is the area for the ethanol. This is the area for the internal standard. Again, we did the same thing for our samples from up above that were our blood samples. And then we calculate the area just as we did from up above. So you take the area of the ethanol divided by the internal standard and you get a ratio number that we will plug into a calibration curve. On your version of the spreadsheet, you will see a column here, and that column will say, okay, what is the percentage based on the internal standard curve? So up here at the very top, this is our equation, and just as before, we will plug the ratio into y, and we solve for x. No difference than what was presented in the last video. So when we do this, 0.1081 equals 0.496x plus negative 0.0006, we're going to get 0.219 in this example for our percentage of BAC. Definitely double the limit or more. So definitely drink. They need to go to jail. Put them in the back of the car and take them down to the jailhouse. And then 0.218, also same reason, same way. Plug it in for y, solve for x. 0.218 is the BAC percentage here. What's different about the QC, though, is that it's the actual column. We know what this is supposed to be. We made it. We provided it to you. We know what these values should be when you analyze them. And those numbers will either be provided to you in an announcement or they will go ahead and be entered into the spreadsheet so that way when you download the spreadsheet, they're already there. If I do not make an announcement otherwise, use the number that's in your spreadsheet. That is probably a change and an update that has happened before I push the spreadsheet out to you for that particular year. All right, so with that said, we know a number, we've received a number, and we got to know, okay, well, what is our error. So that's what these two values or these two columns are over here. How do we calculate percent error? How bad were we when we did this data set? So to calculate error, you're going to take yours and you're going to subtract what it actually should have been. Otherwise, this is called theory. So you take your value, and I might actually change that. I might take this actual and I might change it into a theory value, because that is what it should be theoretically. And then you're going to divide that by what it should have been. So our actual, or of course the theory yield in this case. So if you see that change in the spreadsheet, don't freak out. I guess the more appropriate term is theory, not actual. But it's what we actually made in the lab. It's what we actually gave to you. It's what you actually ran. So that's the value that is the target. So we're going to take the difference, and that difference is actually called the error. And then we're going to divide by what it should have been, and we're going to multiply by 100 because this wants percentage. So if I did that using these values, it looks like we obtained 0.219 in the lab, and it should have been 0.200. And then we're going to divide it by what it should have been, which is 0.200. We're going to do this in baby steps, and then here in the last leg, we're going to multiply by 100. So I'm going to do this with a calculator first. Again, it's always important, do them in individual steps at one time. So 0.219, and then we're going to subtract 0.200 from that. And then we're going to divide by 0.200 and then hit enter. And that's the value that I get. And then I multiply by 100 because we need percentage. And I get 9.5, give or take a little bit, percent off. So I'm less than 10%. 10% is pretty good. Some laboratory methods will let you go to 15%. But lower than 10% is a pretty lab standard, and this is an excellent job. So that means if I feel good about the QC, I can also feel good about all of the blood samples that were ran along with the QC. It just gives me a better feeling in my gut that what we did was proper because we got the right answer here for the quality control samples. In addition to that, it also makes me feel really good because we corrected for the headspace autosampler. So any autosampler actually would be treated this way, but this autosampler, there are chances it slips up every now and then. So that's why we did an internal standard with this particular data. So if I'm going to key this in, I can key that into Excel right there. You can see how I did it. I just took equals ABS. You don't have to do ABS. ABS is an absolute value. So if it turns out to be negative, it just gets rid of the negative and it reports everything as a positive number. Not a big deal if you don't put it in there and you give me a negative number. That just means that your percent error was on the low side and not the high side. That's all that matters. That's all that means. So we're going to do the absolute value of the differences. So you can see the blue and the red. So I clicked 0.219 minus 0.200, and I put parentheses around that. Then we divided by 60, which is what it should have been. So 0.2000. And then we multiplied, so times 100. And then when I keyed that into the Excel, it gave me 9.6. All right, so 9.6 for that one and 8.8 for that one. It looks like that's how that's going to wash out. And then what you'll see here to the side is a random standalone number under the percent error column. And this is just an average. That's what this is. So again, in an updated template, I will give you the average so that way I can mark it appropriately. And it is just the average of these two values. So if I click that cell, it looks like equals average. And then I just click and drag down, highlight these two numbers and hit enter. So that way it will perform that calculation for me. Once more, as before, I'm probably going to get rid of the original curve. So those columns are just not going to appear at all for you. So that's less work that you've got to do. But the reason that we did that in the past is to compare the values we get from the regular calibration curve to the internal standard curve. So here's the story, folks. There's the BOC or BAC. Whoo, gosh, I talk so much, I'm making myself crazy. But this is the BAC lab and how we process the data. And a couple of take-home messages here. Number one, a review of internal standards, especially if you've taken the 150 course. Now, I think you might have a better idea of why we do internal standards and how we handle those. So every time we run something with an auto injector or an auto sampler, we like to have internal standards just to make sure that our injections are taking place accordingly. The internal standard is the more appropriate calibration curve to use because it should correct for those fluctuations and it should give you a better regression line anyway. That means that we've got to do everything based on ratios, and as we saw with one of our standards, if you forget to put the internal standard in, we cannot do anything with that standard. It is a loss. If you forget to put internal standard into your samples, we can't do anything with it. It is a loss. The internal standard has to be present no matter what. We had a bogus standard here that was made. The area just didn't quite make sense, so we kicked it out. We just knew that because it was like hundreds of thousands when our highest standard here was 13,000 instead. Those ratios get plotted on the y-axis. The concentrations get plotted on the x-axis. We generate a calibration curve, and we determine that this one, sure enough, was a little bit better. Then we use that regression line in order to calculate for all of my samples that fall down below, including the quality control. If the quality control gives me 10% error or less, then it probably means that my samples are 10% error or less. All right, so I think that's all I need to say about BAC. Oh, gosh, mighty. I mean, this has probably been one of the longest lab videos that we have ever done in my life. But it's okay. There was a lot of stuff that's going on. Just keep in mind that your lab data is not the same as I entered in here. You've got to go by your batch. You've got to go by what your samples are telling you. Even up here in the dilution section, you've got to go by what we actually did when we did the videos. So with that said, good luck on the BAC analysis and the spreadsheet. There's going to be a couple of Canvas questions that you're going to have to answer that will be toward a lab grade. And then there's going to be a spreadsheet that adds on top of that that will also count toward your lab grade. So make sure that you pay attention to details. Make sure that you are running and reading these reports the proper way. Make sure you don't get cross-eyed and pretend like, oh my God, I need 5.5, but I accidentally used the 4.49 number, because that's going to set off a chain reaction that will start giving you incorrect answers all the way through the spreadsheet. So just be aware, double check all of the lab data. All right, guys, so have fun. This is blood alcohol advanced level. It's probably more than what you needed, but at the same time, I think it gives you a nice flavor of how instrumentation is used in a forensics lab environment. You know, a lot of times what our students and graduates would see would be this type of analysis. They're not going to be doing fingerprinting. They're not going to be doing too much of blood identification or any of that kind of thing. It's going to be mainly the chemical-based tests that involve instrumentation, equipment, chemical reagents, and so forth. That's really our arena. And we leave the other stuff up to the biologist and the forensic analyst. So with that said, if you've got questions, please let me know. And enjoy the playlist. I hope you have at least. And good luck on the spreadsheet. So until the next lab, I'll see you then.